Good morning, class. Now, in this video, let us derive the relationship for the Prandtl number when it is less than 1 by using the integral method in thermal boundary layer, right? So, if this is the case, right, if Prandtl number is less than 1, then we can say that del thermal boundary layer thickness is greater than that of hydrodynamic boundary layer. So it will look like right, and this is V, the delta, and this is delta T, right? And you can clearly show we have to analysis upon the thermal boundary layer. So at thermal boundary layer, the velocity component is V infinity, right? Because at this stream you have V infinity and T infinity. So by using the integral method, let us try to make a relation out of this case, right? So I'll start with your energy equation. With this, let me also write the continuity equation here. So by using the integral method, what we are doing, we are integrating this whole terms from 0 to delta T with respect to y, because this direction is y, right, and this is the x direction. Right? So by using the integration with the parts, this is the first part, this is the second part, so we can write this as Vt minus dv by dy with t dy 0 to delta t, right? And if you see this term, we have to calculate the value of this term, and this term is nothing but minus du by dx from where the continuity equation, right? So I'll write this equation as u dt by dx into dy plus, now this can be written as du by dx into t dy, right? And this term is plus v of delta t, t of delta t minus v of 0 and t of 0, right? And what is the value of this v at delta t? So it will be that is dv by dy is equal to minus of du by dx, and this term will be, if I integrate this with respect to dy, so I'll get v at delta t is equal to minus of du by dx dy, right? So I'll replace this term here, and this will be vanishes because v0 will be 0, so it will be multiplied by any kind of temperature, so it will be the 0 term. And on that side we have alpha dt by dy from 0 to delta t, right? So I'll get, this is a form of ut dy minus, this is t at delta t du by dx into dy, right? And on this side we have at delta t minus at y equal to 0, right? So this term will be 0, and the value of t delta t means t at this point delta t is t infinity, so I can write in place of t of delta t as t infinity, right? Now here, so we can write this as u is t infinity minus t by dy is equal to alpha at y equal to 0, right? Now again the same thing what we did in hydrodynamic boundary layer, we'll get this differentiation out of this by using the Leibniz rule. Now Leibniz rule says what? Again I write it. Right? Now in this case, if you see, your function is u t minus t infinity, where a is 0 and B is delta t. So by putting these values here, these will be 0, so we can easily take differentiation out of this function, right? So this is the Leibniz rule, and if I apply this Leibniz rule here, what I'll get? I'll get right. Now in this case, if you remember, we have to deal with your theta term, which is a temperature gradient, and if I, in this equation, if I do T infinity minus Tw plus Tw minus T divided by T infinity minus Tw of dy is, and instead of T we can write as T minus Tw upon T infinity minus Tw. So this is theta, so I can replace this with respect to theta. So what I'll get? I'll get d by dx of this is 1 minus theta is alpha by d theta by dy at y equal to 0. So again this is your relation which you have to remember, right? Because I am solving this by using one of the profile conditions. I have taken the polynomial values up to third order of, right? You can take it at single, you can take it at double order, you can take it at the fourth order, so you'll get the different relations out of it, right? And as we solved in case of hydrodynamic boundary layer by using, if you remember, this equation, now here I have to solve it for theta, right? So same conditions. Now here the boundary conditions, how will it change in this case? If I have to write in case of thermal boundary layers, right? So I'll just put it the conditions, and I try that you will try to solve this for the thermal boundary layers. I'll directly put the relation here and I'll solve further, right? So what are the boundary conditions in this? At y equal to 0, boundary conditions, right? You can say that T is equal to Tw, right? Second, at y equal to delta T, T is T infinity, right? And third condition, at y equal to delta T, there is no change in this at the thermal boundary layer. And the fourth one, at y equal to 0 will be 0, right? So by taking these 4 boundary conditions and the same equation as so I have taken up to third order. You can solve it for second order also, then you get the different relations. You can get it for first order also, you'll get the different relations, as well as for the fourth order you'll get the different relations. So by using these 4 boundary layers, I have to solve it for third order, and after getting these values, so I'll get as theta is equal to again 3 by 2 of y by delta t minus half y cube by delta cube, right? So also I need to differentiate with, because I'll need that relation, so I'll differentiate with respect to y at this condition, right? So it will be 3 by 2 of delta t minus, it is 3y square by t delta cube, right? So we'll use this relation also in our final compilation, right? So this is the theta which you are getting after solving this. So it is your homework, right, to get this solution, right, as we did in the hydrodynamic boundary layer. So if I put this into our equation, which is, let me write it once again, of 0 to delta t is u 1 minus theta of this as right. Now you know the theta. Now what is the value of this u at this point? It is u of infinity. Remember, if you see at this point, the value will be u infinity, because u infinity will come from this point. This point onwards, it is a u infinity. So now let us solve this. I'll put this value, it is 1 minus 3 by 2 y by delta t plus half y cube by d delta cube into dy is, now at y equal to 0, so this term vanishes, right? So I left with 3 by 2 delta t with this, right? Now again, if I want to get this, I have to integrate this. Now upon integrating it, what I'll get, this is a constant, so it will come out, right? And we have a dy dx of 1, the integration with respect to dy is y minus 3 by 2 y square into 2 by delta t plus y the 4 by 4 delta t cube as 3 by 2 of this delta t, right? So if I put the values in this case, so what I'll get, if I get it out as, so it will be u, I'll get delta t minus 3 by 4 delta t plus 1 by 8 again of delta t, right? And 0 with respect to is 0, so it will be 3 by 2 of delta t, right? And if I get it delta t out of it, it is 1 by 3 by 4 plus 1 by 8 is 3 by 2 alpha by dt, right? And by solving this, I'll get 3 by 8 and I'll write as 3 by 2 alpha by delta t, right? So I'll get delta t on this side. So delta t d delta t is 3 cancels, 8 by 2 alpha right, alpha by this into dx, right? And again if I integrate it, so I'll get by 2 on integrating plus c1. So this 2 cancels, right? And if I take the boundary condition here at x equal to x0 is 0, so you'll say that dt is 0. So by this we'll get, and this is a special case, right? So c is 0, so I'll get delta t square is 8 alpha x by this, right? And if I do this thing x square sorry, it is x by x square, so this x cancels, so I left with delta t by x square is 8 by this upon u infinity x, right? So if I put this relation, right, what I do 8 alpha, I multiply and divide by the kinematic viscosity, right? And if I do this, this will become 8 mu by alpha by mu, right? So this delta t by x is nothing but root of 8. This is what Reynolds, this is what Prandtl. So it will be Reynolds number the by half into Prandtl number the half. So this is the relation of delta t by x in case of your sorry, this is the relation which you get out of it. And if you do the square root of this, so it will be root 8 Reynolds number the power half into Prandtl number the power half. So this is the same result. If you remember, while doing the order of magnitude analysis, we'll get this thing. It is a function of Reynolds number the power half into Prandtl number the power half, right? And now it is a more accurate answer in this case, so we'll get this thing. Now here again I want to calculate the Nusselt number in this case. So to calculate the Nusselt number, let me do that. Whatever is the temperature gradient, right? This is the heat conducted for the fluid must be equal to H of heat convected. So this is d theta by dy at y equal to 0 as H. And if you remember this d theta by dy at y equal to 0, we put this as 3 by 2 of delta, right? So it will be kf times 3 by 2 of delta T is equal to H. So in this case, H delta T by K is nothing but 3 by 2, right? So by taking this analysis, and we also know that the Nusselt number is nothing at x is nothing but hx by k, right? And if it is hx by k, so can I multiply and divide by the delta t? Yes. And while doing this, this term is 3 by 2, right? And it is, I suppose, minus. So I'll check it once again this. So it will be 3 by 2 of, let me write, x by delta is 1 by root 8. You can say that root 8 of Reynolds number the power 1 into Prandtl number the power minus 1, right? It is in under root. So I'll get the Nusselt number is 3 by 2 root 8 of Reynolds number the power half into Prandtl number the power half at x, right? Now in next video we'll analyze case 2, right? When Prandtl number, now this case is for what we did for the Prandtl number value is much less than that of 1, right? So we have to now derive again the same by using integral method the relationship when it is the case in our next video, right? So thank you.